Hello all. In this video, I am going to talk a little bit about convolutional neural networks. So this is a particular kind of modern deep learning machine learning algorithm. It's been around for about really in prominence about 12 years, maybe a little longer than that. 14 isn't quite beyond that. But this is a model that was invented not super long ago, and it totally revolutionized the field of computer vision, so that more people are working with these things in machine learning than are actually working on those algorithms that we've studied before. Now, the algorithms are still important because there are times and places where machine learning can't be used, where we don't have the data, or these machine learning models are large. So if you're working in a place where you don't have good computer processors, you may not even be able to run a model that's been trained, much less train a model. So they require a lot of resources to train and to run, and that means they're not always the right solution. Sometimes they're too slow as well. Sometimes we want something that's more real time than they can be. But they also allow us to do all kinds of things. They can do object detection, they can do face detection, they can do image classification, and they are the building blocks, the methods that are used in a convolutional neural network are the building blocks even for generative AI. So they've allowed us to get to this world where we can generate images. Let's take a look at what a convolutional neural network looks like. So it's designed to process images or other matrix-like data. What the details are can vary, but there tends to be these sort of two big sections to the model. The example I'm showing here is a classification task. So we have a picture coming in. It looks like a picture of a car. And what we want is that the data flows through this model that manipulates it and changes it in ways that I will talk about in a second. And then out the other end pops a category. What we would like is for car to be on and all of the other categories to be off. We call that one hot. It's a term that comes from electronics. We have a set of wires and only one is on. In this case, it means that when it produces an output, we want to interpret that output as having one unit on and all of the others off. And our correct answers, this is supervised learning, we have to provide a correct answer. Our correct answers need to look like that too. There are lots of other tasks that can use these pieces or use part of a convolutional neural network as part of what they do. And we'll talk about those another day. So let's take a look at this image right here. I love this image because it's very stripped down and simple, but it has all the parts of a convolutional neural network, like the main ones are right there. It also shows up everywhere. I did a search at one point to figure out who created this image because I wanted to attribute it properly. I believe it was MathWorks. Those are the people who create the programming language MATLAB and its tools. MATLAB is one of the other primary computer vision systems that is out there. That was the oldest reference I could find, but I'm not absolutely sure they created the image. So we're going to work with it anyway. All right, so what you can see is there are two main sections here. There's the section that's labeled as feature learning, and there's the section that's labeled as classification. This section right here, this is really a traditional, old school, goes back 50 years or more neural network. And those exist in machine learning, and they're used for a lot of different tasks. They take in an array of numbers, a vector of numbers, and they pass it through a number of these layers that are also vectors of numbers, and then they produce an output. So this is sort of your traditional kind of neural network, and its task is to perform the classification task. One of the issues we have had in the past with these is that these networks don't work really well when you have like an image that has 100,000 pixels. Or 100,000 values when you include all the different colors. It would overwhelm these and they couldn't actually learn anything. So it's really important that we have this first section, Because in the old days, what you would do is you would try to extract features by hand from the picture using the tools like edge detection and all these other tools that we've already learned, and then you'd make a representation of the picture that you could put into a machine learning model. Convolutional neural networks were revolutionary because they take that step away from us and they make it something that the model can learn itself. So here it's learning how to categorize. All of these earlier layers, they are extracting features from the image. But the trick is that initially, these are all set to random values. They are extracting random features from the image. And as the model sees examples, it slowly learns which features are useful for performing the classification task. So the model determines what features to use without any human intervention. And then those features are used to do the categorization. It's kind of amazing. All right, so at the beginning we have our picture. We talked about convolutional filters. If you think back, we talked about blurring and we talked about edge detection specifically that were convolutional filters. If you remember what happened when the convolutional filter, you'd look at a little neighborhood in a picture and you would have this kernel, which was weights, and we'd do a weighted sum of the values in that neighborhood, and then that would be the result that would go into our output, our feature map. That's what's happening here, except that initially those kernels are all set to random values. So we don't know what they're finding. But we have, in the convolutional layer, some number of different, completely independent convolutional filters. Each one operates on the input image and produces a new version of the image, much like the blurred picture or the edge detection picture or something like that. We get this new feature map that has extracted some sort of feature from the original one, and we just stick those all together as if they're channels. So if I had, say, 32 different filters in this first layer, I would end up with something that's more or less the size of the input image, maybe slightly smaller, and then it's got 32 different layers stacked together. We don't have to look at them. They wouldn't look like much to us, but it works as a way of collecting up the data. The next thing you do, you will see different architectures. Sometimes they will take the result of that one round of convolutional filters and they'll run them through another set of convolutional filters that are looking for patterns across the feature maps, potentially. So there might be something going on in feature map 10 and something going on in feature map 22 that happens to be important as a correlation, and you can have another convolutional filter that notices those things happening and marks them as interesting. But what the diagram is showing us is the main other thing that we do, which is we scale down the picture. We call it pooling. There are different variations on exactly what that means, but fundamentally we look at a little patch of the original image and we only keep one value out of that patch. Max pooling is the most common. You look at the region, you keep the largest value, and you pass that along to the next layer. These, you don't necessarily do overlapping regions, unlike the convolutional filters. You just kind of divide the whole image up into patches, and for each patch you keep one number. So if I have 2 by 2 patches and I do max pooling, the resulting image will be half as wide and half as tall as it was originally. And you can see that is in the way this is showing that it's been scaled down. The next thing that happens after that is another convolutional layer, which is going to look across all of those scaled down features, and then it does convolutions. We get more layers of the output of the filters. We do more pooling. You get this kind of cycle that happens. So why do we scale down the images? Well, there are really 2 reasons. One reason is if we took this big thing and we ran a whole bunch more filters on it, we're going to get this enormous collection of data. It's just going to be gigantic, potentially. So we don't want the amount of data that the model is working with to blow up as we go from layer to layer. So scaling down the data by pooling is one way to control how much data we have. But that's actually the lesser of the reasons. It turns out that convolutional filters tend to work best at a relatively small scale. So 3 by 3 regions, 5 by 5, maybe 7 by 7, or maybe in an extreme 9 by 9. We're only talking 9 pixels by 9 pixels. That's tiny. Suppose that you have a feature that is just too big to be seen at that scale. Like the pattern is happening, but it's happening on the order of hundreds of pixels, not tens of pixels. How can we detect that pattern? Well, it turns out to be harder to make the filters bigger, so we make the image smaller instead. So by scaling down the picture, we allow the system to detect patterns that are initially too large for them to be seen by the filters that we have. And so we have these realms of scaling things down. This is called creating an image pyramid. It actually shows up in other places in computer vision, but it shows up particularly in convolutional neural networks. All right. If you note in my notes, I go through each of these layers, a convolutional layer and the pooling layer. I've kind of talked through that already, so I'm just going to scroll through. There are some other kinds of layers to note. This example does not actually have any of these layers called dropout layers. Dropout layers we add to help with overfitting, and we'll talk about those when we get into practical terms. But they're not learned, they just kind of sit in there, and what they do is they block some of the data from passing through. They just zero out some of the data. And in practice, that forces the system to generalize more. I also haven't talked about the fact that this output layer is called a softmax layer. The way that works is each of these units has some value initially, and then we scale them so that they add up to 1. They're all numbers between 0 and 1, and when you add them up, they add to 1. By doing that scaling, we sometimes end up thinking about these as a probability. What's the probability, according to the model, that the input was a car? So maybe we have 0.7 here, and then like 0.2 for the truck, and then small values for the others. Softmax is the most common output layer for these kind of models. Because it's kind of handy to have that, we can treat that number as a confidence, right? So if it's only 0.7 confident that it's a car, it's not really confident. If it's 0.99, then we can say it's really confident that it's a car. It also allows us to do some other math. But when we compute accuracy on these models, with the softmax, we just look at which of these outputs has the largest value, and that's the one we assume that it's making. So even if it was 0.51 and not very confident at all, we would still say that's its choice for what the category is, and we use that to calculate the accuracy. The last thing I want to talk about are a couple of actual real-life models that people have created, and just to show you that they can vary tremendously in their size and complexity, and how we view them as well. So this is a diagram showing the VGG network. This is a classic architecture. With the library we're using, you can actually say to it, hey, give me a VGG network, and it'll just hand you pre-built one of these, so you don't have to build them for yourself. What you can see are the white layers are convolution, and the red layers are pooling, and then these are the fully connected layers at the end. So it's drawn slightly differently than the earlier diagram, but it's showing us very similar things. It does 2 convolutions and then a pooling, 2 convolutions and then a pooling, 3 convolutions and then a pooling, and so on. Repeat it a few times, and then it's done. And this was particularly shown, it shows that there are 1,000 output units here. 1 by 1,000 means that output line is a one-dimensional array, and it's 1,000 long. There was a classic data set called ImageNet that all of these models have been tested on. ImageNet had 1,000 different categories that it could classify images into. So that's why you'll often see these examples where they show it with an output of 1,000. This is a fairly small neural network, a fairly small convolutional network. It's just not super big. At the other extreme, you can see this is a picture that shows the Google Inception version 3 network. So each of these slabs, these like rectangular prisms, whatever you want to call them, Each of those is represented by a little rectangle in the lower picture. So there are a lot more rectangles here than there are with VGG. Uh, and this was actually also producing, it says 8 by 8 by 2048, which was then transformed into 1001 categories, which was, again, it was trained on the ImageNet network. So you put in images here that were 299 by 299 by 3 in size, quite small actually. And the output of this was this big chunk of data, which could then be used to categorize. This is just giant. Inception is just a very large model. And people have not continued to make larger models since, mostly because it's really hard to train Inception, and it's hard to even run it. Like, regular laptop might not be able to run it very effectively because it's just so large. You put an image in one end and it has to flow through all of these calculations, all of these matrix operations until you come out the other end. So since Inception, this version of Inception, there's been much more work on whether we can actually do as much with cleverer, not so big models. And that's kind of been a focus. All right, so what are we going to do with convolutional neural networks? We are going to work with CNNs on a classification task. And what we'll do is in the in-class activity, I will walk you through a really simple classification task. I'll show you all the code that you need. It's all scripting. There are very, very few functions that we're going to create for this. And then you will have another data set, and you will figure out how to modify, with some guidance, how to modify those earlier code examples so that you're training on this new data set. Because training convolutional neural networks is expensive, it's really hard for an ordinary laptop to train a model without it taking forever. We are going to show you how to use a cloud tool, Google Colab, which is free, that allows us to write the programs in our browser, and then we run them in the cloud. So essentially, Google is kindly allowing us to borrow time and resources from their data centers. So we get to use their fancy GPUs. Now, we're using the free version. There is actually a Google Colab Pro, a slightly updated, upgraded version that's available for students for free. So if you find that you need it, you can do that. But otherwise, we'll use the free version. It comes with limitations. There's only so much processing power that it'll give us. There's only so much time they'll give us training on the cloud and so forth. But I'm going to, in another video, show you how to actually work with Colab and how the programming works in that context, because it'll look a little different. But the nice thing is, it doesn't matter what your laptop is, we're going to be running things in the cloud. All right, so this has been a really quick introduction to convolutional neural networks. If you remember the overall gist, that we pass in an image, and then it goes through a feature extraction phase, and then another stage that figures out the category. The details of how that happens are not super critical. As you're working with the examples, hopefully some of those details will resonate and make sense to you. Working with these is exciting and fun. You can do some really amazing things without having a huge amount of coding background. So I hope you'll dive in and enjoy this, and I will see you again very soon to talk about Google Colab.